Swayam Prabha. Digital India. Educated India.
So, this class I am going to start a new topic, that is lateral loaded pile, and in this module I will also discuss the pile under uplift. So, first I will discuss about the lateral loaded pile, then I will discuss about the uplift pile, and then as I have already discussed that pile can be subjected to compressive load, pile can be subjected to horizontal load, pile can be subjected to uplift also. So, that means pile can carry the incline load also, horizontal load. For example, the foundation for retaining wall, where the lateral load or the horizontal load will come on the foundation. Then bridge, abutments, and if there is an wave which is coming to the structure, then those type of structure will be subjected to horizontal load. Now, if the horizontal load acts perpendicular to the pile axis, I mean if this is the vertical pile axis and it is acting perpendicular to that pile axis, then that type of load is called lateral load, and that type of pile is called lateral loaded pile. So, the application area as we discussed that because the pile under compressive load, which is very common, then under lateral load, retaining wall, bridges, abutment, waves, then uplift for tall structure or for tower. So, where uplift load can be subjected to pile. So, first I will discuss the pile under lateral load, and then first I will discuss the ultimate lateral load carrying capacity of piles. So, I will discuss the ultimate lateral load carrying capacity of piles in two types of soil. First one is the cohesive soil, and then the second one is for cohesionless soil. And I will also discuss the lateral loaded capacity of the pile for two types of piles. One is the short pile, one is the long pile. So, in general, that if pile is subjected to lateral load in cohesive soil, then we will get this type of distribution. Okay. So, what is this distribution? Suppose if this is the pile which is subjected to lateral load P. So, this is subjected to a lateral load P, and then this pile will get a resistance from the soil, because it is moving in the lateral direction as the load is applied in laterally. So, it will get a resistance from the soil. So, that type of resistance is drawn, or the pressure that pile will be subjected from the soil due to the lateral movement, that is also represented here. So, we can see that this pressure distribution it starts from 2 cu to 8 to 12 cu at the base of the pile. Okay, CUD. Okay, so, it is 12 CUD. So, 2 CU from the top, it will go up to 8 to 12 CU. So, if I multiply it with the D, then that will give you kilonewton per meter, because actually this CU is kilonewton per meter square. So, now if I multiply with D, then this will come at kilonewton per meter. So, top also you can multiply it with the D. So, that means actually the distribution is 2 Cu to 8 to 12 Cu at the base of the foundation, and it is also noticed that approximately after the 8D from the top of the pile, the distribution is uniform. So, and it is also observed that for the short pile, lateral capacity depends on the soil resistance. That means, the soil resistance is given the whole lateral resistance for the lateral loaded pile. So, lateral capacity of the pile solely depends on the soil resistance for short pile, but for the long pile, lateral capacity primarily depends on the yield moment of the pile. Okay. So, based on this distribution for the lateral loaded pile under in clay or cohesive soil, that means there will be a uniform distribution of the stresses or the resistance, soil resistance after approximately 3D. This is 3D, D is the diameter of the pile from the top of the pile, of top of the ground surface. So, this is D is the diameter of the pile. Okay. So, based on that, Brooms proposed different soil pressure distribution for short piles and the long piles, pile in cohesive soil and the cohesionless soil. So, I will discuss the first, the Brooms theory. So, Brooms has suggested different pile soil distribution for different types of piles. That means, pile can be, as I mentioned, can be short pile, long pile, it can be free headed, it can be fixed headed. Okay. So, first I will discuss about the piles in cohesive soil, which is a free headed pile and it is a short pile. As for the Brooms theory, that if this is the ground surface, okay, and we have a pile which is a short pile and which is subjected to lateral load, which is say HU. HU is the lateral load. This pile is subjected with the eccentricity E from the ground surface. That means, from the ground surface above a distance of E, H is subjected to the pile. So, now this is the length of the pile L. Okay. So, now as per Brooms theory, as it is a short pile, so pile will rotate about a point within the pile. So, this is the rotation of the pile. So, it will rotate about a point within the pile. So, this is the deflection pattern. So, this is the deflection pattern and this is the ground surface. Okay. Now, based on that, the distribution, soil pressure distribution will be something like this. So, this is the point. So, you can see that pile is rotating, the short pile under cohesive soil, it is rotating about a point within the pile. So, upper portion of the pile is moving towards the soil. So, that means, upper portion pile, it will give the passive resistance, because it is moving towards the soil from left to right. So, upper portion there will be a passive resistance that will also act from right to left, but below the point of rotation the distribution will be totally opposite. Now, the lower part, the pile is moving from right to left. So, the reaction or the passive resistance of the soil will act from left to right. So, that I will write here. So, I will draw here. So, this is the point. So, below that there will be a distribution like this. Okay, and above that there will be distribution like this. Okay. And Bromes has suggested that there will be 0 soil resistance at a distance of 1.5 d, where d is the diameter of the pile from the ground surface. Okay. Because if you see the actual distribution, that distribution is, or that value is very small. So, that is why it is mentioned that it is recommended that the top portion 1.5 d, there will be no soil pressure resistance, and then or soil pressure or the resistance, and then there will be a uniform resistance. Because you can see it is for the cohesive soil, this soil resistance is more or less uniform after a certain depth. So, here the Bromes has assumed or recommended that the from top 1.5 d portion there will be no resistance, after that there will be uniform resistance, and as expected above the point of rotation the resistance will act from right to left, and below the point of rotation it will act from left to right. And this is the pressure distribution diagram. So, if we can write that this is the point A at a distance of f, where maximum bending moment within the pile is observed. So, that maximum bending moment will be at the point f. So, after that it will go like this. So, at the point there will be a maximum bending moment, and that point is f. So, I can write that this is M max, okay, which is at a distance of f, or total, which is this is 1.5 d. So, total will be 1.5 d plus f from the ground surface, and this distance is g plus 2, and this is also g plus 2. This is not in scale. Okay. Okay, so, this one is total, I can write this distance is g. So, total length of the pile L I can represent is equal to 1.5 d plus f plus g. So, this is a equation. The total length is 1.5 d, up to which there will be no soil reaction, then plus f, at that point there will be a maximum bending moment, then plus dg is the rest of the portion. So, total L I can write 1.5 d plus f plus g. Okay. So, now for the short pile, this is the pressure distribution, bending moment diagram, bending moment and the deflection pattern. So, I can write this is soil reaction and this is I can write bending moment. Okay. So, if I want to determine the what would be the HU value, HU is acting laterally, but if I look at the soil reaction diagram, then G plus G divided by 2 this part and the G by 2 and the upper part, these two will cancel out. So, the HU will get from the F up to the F portion only, small f portion only. So, I can write that HU will be equal to, because this G by 2 will cancel out. So, this will equal to, and another thing that I want to say that from this diagram, this uniform portion is varies from 8 to 12 Cu. So, Bromes has recommended that this value is 9 Cu, and then we can multiply a d. 9 Cu is kilonewton per meter square. So, this stress I can represent per meter. That means, if I multiply with the diameter of the pile, so it will be kilonewton per meter. Similarly, this one is also 9 CUD. So, it is 8 to 12 is general range, and Bromes has recommended that we can take a uniform soil reaction of 9 CU and d is multiplied along the length of the pile except top 1.5 d portion where the soil reaction value is 0. So, I can write the HU will be that 9 CUD into F, because 9 CUD is the that pressure distribution into F zone it is acting, because G by 2 is cancel out. So, that region or that area within the F 1.5 to F distance. So, that is giving the soil resistance or the lateral load capacity of the pile. So, this is the equation number 2. So, ultimately I want to calculate the HU, what will be the HU value. So, next if I take the moment maximum moment. So, M max. So, what is M max? So, M max is, because M max is acting at F point at a distance of F from that 0 pressure point. So, maximum if I take the moment at this point F point and then I can get that the maximum moment will be how much. So, there will be HU into 1.5 D plus F plus E, okay? Because this is HU F plus 1.5 D plus E, then that is acting, and then the upper portion there will be soil reaction. So, minus soil reaction area 9 Cu D F, and I am taking moment from this point, or I should say this is the F point. I am taking moment from this F point, because where the moment is maximum and I am determining the maximum moment. So, F into this area divided by, it will act as the center, F into F by 2. So, that is the maximum moment. If I take the moment at point F, I am taking the moment above the point F. So, this is M max. So, if I simplify this equation, I can write that M max is equal to see, after simplifying this equation, I can write HU is 1.5 D plus F plus E, and this is 9 Cu D F is equal to HU. So, minus HU into F by 2. So, finally, I can write this is HU E plus 1.5 D plus, there will be F, this is F minus 0.5 F. So, this will be plus 0.5 F. So, F 1 minus 0.5, so 0.5 F. So, this is equation number 3. So, there will be a maximum moment we can calculate at the point F. So, where this is the value. So, I can calculate maximum moment in another way also, by taking the moment lower part of F. Okay? So, because this will also give me the maximum moment. So, I can write that for the lower part, that 9 Cu D into G by 2, this is the area, and then the lower part total, this will be G plus 2, then plus G divided by 4, that is for this part, then minus G divided by 4. Okay. So, G divided by 4 will cancel out. So, because what I am doing, I am taking the moment, maximum moment, and for the lower part of the F. So, this is the lower part, we have two rectangular soil reaction area for height G by 2 each, and both are acting in opposite direction. So, that is why I am taking the lever arm will be for the lower portion will be g by 2 plus g by 2 divided by half or divided by 2. So, that is g by 4, then minus g by 2 divided by 2. So, that will be g by 4, okay, for the upper part and the lower part. So, finally, this value is 2.25 d g square into Cu. So, this is also M max. So, there will be 4 equations. So, now what are my unknowns? My unknowns are F is unknown, I do not know what is the F value, G is unknown, M max is unknown, HU is unknown. I mean 4 unknowns are there. HU, because D is known, diameter of the pile is known, length of the pile is known. So, D is known. So, unknown are F is one unknown. So, what are those unknowns? F is one unknown, G is one unknown, HU is one unknown, and M max is another unknown. So, we have 4 unknowns and we have 4 equations. So, once we solve these 4 equations, we will get the ultimate load carrying capacity of the pile HU. Then we get where the maximum moment will come, and then what is the value of G, and then maximum moment Mx also we can calculate. So, this way after solving these 4 equations we can get what will be the HU value. HU is ultimate load carrying capacity of the pile. Lateral load. Okay. So, next one I will discuss that this is for the short pile, but short pile remember that M max cannot be greater than M y. That means, y is the yield moment of the pile moment of the pile. Okay. So, for the long pile what will happen, this is for the long pile, previous one for the short pile, and for the long pile same. If I take the ground surface, this is the ground surface and we have a pile which is the long pile. Okay, here also HU is acting at a height of E, and here again this is the L length of the pile. So, here the total pile will not rotate, because the lower as the pile is long. So, the lower part of the pile will be very rigid, it will not move like the short pile. So, what will happen, the upper part of the pile will move, and after a certain point if we apply a more HU, then there will be a break or yield of the pile at a point, and that will happen if the developed moment within the pile is greater than the yield moment of the pile material. Then this yielding of the pile will occur at a point. So, that point is this point where there will be a yielding of a pile, okay, and this point the maximum, at this point maximum bending moment will develop. So, at this point maximum bending moment will develop, so at this point maximum bending moment will develop. This is the bending moment diagram. Okay, and definitely this is M max, maximum moment, and definitely this, if M max is greater than M y, then there will be a breakage or the yielding at this point within the pile. So, we can draw the soil reaction. So, again for the soil reaction, top 1.5 D portion there will be 0 stress, then uniform stress up to that point, then this stress will change and this will be the soil reaction for this long pile. Okay. So, I can write, so this value is again that uniform portion value is 9 cu d and this distance is again where the maximum moment is acting is F. So, F is this one and this one is 1.5 d. So, this is the deflection for the long pile. This is the soil reaction and this is the bending moment. Okay. Now, for the long pile, I can write that previous equations can be valid. Which are the previous equations? Because equation number 1 is valid here also. Okay. Equation number is valid here also, because here or I can write a different equation, but here also equation number 1 is valid because this is G. So, this is equation number 1 is valid here. Equation number 2 is also valid here. Equation number 2 is also valid here, because we can assume that this portion and the lower opposite portion are counting balance these forces. So, this portion are balancing these forces and then this top portion is only giving the HU. So, equation 2 is valid, equation 3 is also valid, but equation 4 is not valid. Okay? Equation 4 is not valid here, because we cannot write equation 4 here. Okay. So, we can write equation 1, we can write equation 2, we can write equation 3. So, what are the equations are valid here? So, this equation 1. So, that means for the long pile L is equal to 1.5 plus F plus G. So, I am writing again 1, 2, 3, 4. So, 1 is valid. Again, as I mentioned that this top portion reaction is equal to HU and the bottom portion, the positive negative side, we are assuming that they are balancing each other. So, the equation 2 is also valid. So, equation 2 we can write that means HU will be equal to 9 CUDF. So, this is also valid. Okay. Then you can take the maximum moment value at point F. So, this is point F. So, that will be equal to, again we can write HE into 1.5 D plus F plus E minus this one 9 CUDF into F plus 2. So, that is also valid. So, this equation, this value is coming out to be, this value is HU. So, this is HU. HU, then E plus 1.5 D plus 0.5 F. So, this is also valid. What are the unknowns? Again, F is unknown, G is unknown, HU is unknown, M max is unknown. So, there are 4 unknowns 1, 2, 3, 4, but there is 3 equation, because equation 4 is not valid here for the long pile, because in the equation 4 lower part we cannot take that type of moment expression, because it is not uniform. Distribution is soil reaction is different as compared to the short pile. So, equation 4 is not valid. So, there are 3 equations for the long piles, but we have 4 unknowns. So, we need one more equation, and that equation for the long pile, that in particular this case we have to consider that M max is equal to yield moment. Okay? So, this is the yield moment of the pile, and moment of the pile, and which is the known value. So, based on the which type of pile section we are taking, what are the material of the pile, this yield moment is known. So, that means this yield moment is known, and that is giving us the fourth equation. So, that means these 4 equations are here, and if the maximum moment which is induced in the pile is greater than yield moment, then the yielding will occur. Okay. So, that we do not want. So, we have to restrict that maximum bending moment to equal to the yield moment. So, that is that means we can go up to this yield moment. So, M max should be equal to yield moment, and that will give us the fourth equation, and yield moment is known for a particular pile. So, and then we have 4 equations and 4 unknowns, or now as the M max is equal to M y and M y is known. So, we can say we have 3 unknowns and we have 3 equations. So, we can solve and we will get the H u value. So, this is for the long pile, and both the piles, short piles and long piles, are in cohesive soil and they are free headed pile. That means, we have not applied any fixity on the pile head. So, in the next class I will discuss that how we can develop similar type of equation for the fixed headed pile when pile is within the cohesionless soil. And then based on these equations, already charts are developed. So, we can directly use those charts, and then we can design or we can calculate what would be the ultimate load carrying capacity of the lateral loaded pile. So, ultimate lateral load carrying capacity of the pile. Thank you.